So a very good afternoon to all of you. So I extend my warm welcome on behalf of Director of the Institute. He was supposed to preside over this lecture, but he had to go for an urgent travel, so I have been asked to do so. So today is it's my great pleasure to introduce today's colloquium speaker, Professor Saptarshi Basu, who is from the Department of Mechanical Engineering in Mechanical Sciences Division. Professor Basu is a very accomplished scientist. He has been here for almost 2 decades now. And Professor Basu is INAE Chair Professor and KS-IIDC Chair Professor in the Department of Mechanical Engineering. He works on multi-phase systems, especially droplets at multiple length and time scales across multiple application domains. His research marries fundamental aspects of classical fluid mechanics like vortex dynamics and swirling flows and the more interdisciplinary aspects of interface transport of droplets in multi-phase systems. He is a fellow of Indian National Academy of Engineering, National Academy of Sciences, American Society for Mechanical Engineers, Institute of Physics, Royal Aeronautical Society, and Royal Society of Chemistry. He has been the recipient of DST Swarn Jayanti Fellowship in Engineering. He has received Distinguished Alumnus Award from University of Connecticut, from where he did his PhD. And also K.N. Sitaramu Medal and Prize from International Society of Heat and Mass Transfer. Recently he has obtained J.C. Bose Grant from Anusandhan National Research Foundation and Rajiv Goel Prize in Applied Sciences. Apart from his fundamental research, Professor Basu also is a co-founder of a biotech startup specializing AI-based point-of-care diagnostics, and he's technical advisor to a tech startup involved in micro-gas turbines. So, and of course, many of you would have attended his talk on space, microgravity travels. So let's listen from Professor Basu today. Thank you. Welcome. Thank you.
Thanks, Satyam, for the nice introduction. And so I have been in IISc for like 15 plus years now, so it's just short of 2 decades. So 5 years more to go. So in this particular colloquium, I thought that I would talk about a little bit about what I do in the area of droplets, particularly focusing on something which is not addressed in the literature so much, which is under extreme flow conditions. And I will get to it, what it means. Special homage to Professor Satish Dhawan, whose birthday is today, actually. And he was the founder of, or the father of experimental fluid mechanics in India. So the reason that I'm here is perhaps because of his initiative, long time back. All right. So, so people normally do the acknowledgement later. I do it first, just because of the fact that people do not have the patience to sit through the acknowledgement. So I call them partners in crime just because I think my students are more brilliant and intelligent than me. So I don't call them advisees. And of course, I have great collaborators over the years and still continuing. And of course, there are a lot of students whose work I'm not going to present, but they are very much there. So I've graduated 25 PhD students, so I mean, all of them are great. Let me put it that way. So these are my partners in crime. So I'm going to present the work mainly in the top row. Okay, so their work I'm going to kind of focus today. So droplets in our lives, if you look at it, so it is everywhere. So if we look at from aerospace, defense, energy, additive manufacturing, spray coating, how they coat the gas turbine blades is done through high velocity oxyfuel coating. So this is a cold spray, how it looks like. This is a spray flame, and this is basically a combustor. So it is there in the industries. And droplets on the other side is used for surface patterning. Say, for example, you want to print something on a surface. It's the opposite to a clean room type of an approach. Okay, it's bottom-up type of an approach. You can also do 3D printing. You can do biomicrofluidic assays and electronics and so on and so forth. It's a huge area of research. It's there everywhere. And this is more on this. So this is done by Siddhant, obviously, over here. So this is like, when you prepare a droplet-based microfluidic type of devices. This we are very familiar with. This is the COVID that we recovered, and it's kind of, created quite a bit of an havoc. Even in agriculture, you can transfer droplets through this vortex mediation. So therefore, you can transfer them to long distances and very targeted delivery. So all these things can happen. So it is there everywhere, from disease to agriculture to everything that you can see. So the idea that I'm going to present in this particular slide is that fluid mechanics is all about scales. Okay, so I am going to do first that these are the velocity scales, so it basically increases. So at very low velocity scale, you have the microchannel flow. This is a drying blood droplet work, which Deepshika will know. So all these things are at very low velocity scale and very small length scales. These are typically of the order of micrometers per second, the velocity. You go a little higher, this is moderate velocity, this is small to moderate scales. This is where you actually have drop impact on certain surfaces, right? So this could be bio-inspired surface, this could be droplet impact on a liquid pool. This is the famous mask work that we did, where you actually sneeze and the droplet comes out atomized on the other side. So these are moderate velocity and very small to moderate length scales, okay? And it goes on that you can also have this vortex droplet interaction. You have something called vortical cleaning. This is flow within a soap bubble that Jatin and Siddhant did. So all these things comes under small to moderate length scales and moderate velocities. You go to real high, which I'm going to talk about today. This is high velocity small length scales. This is basically a shock-induced atomization of a droplet that you can see over here. This is the same thing, but it's basically a combusting droplet interacting with a shock, as it is pertinent in hypersonics and applications like that. And this is basically the sector combustor, which I did with Pratikash, and Thirumalai is here. He is the student. So these are high velocities and very large length scales. It is of the order of meters. Okay, and you can see a high-speed particle image velocimetry of the flow that is inside such combustors. So you can see it spans quite a bit of a length scales and time scales, okay, when you look at that kind of work that we do in our lab. Most of them involves droplets in one way or the other. And you can also put this now in the kind of map, which I guess the first okay, this is our idea that you can have fundamental research and you go on more to application. And these are the scales, so small scale, mesoscale, and large scale. So this is how you traverse all the different applications that we do in our lab. Okay, so this is quite a bit. So you have bacteria-laden blood to vortex porous media interaction. You have swirling flames. You have shock droplet interactions, and so on and so forth. So this is like a map, and I think Niels Bohr was the first to point towards such kind of a map, that how your research should be placed on a matrix like this. All right. So this is where I begin the adventures of a droplet. So I'm a fan of Tintin. So this is the pathway of the droplet. So this is one of my students actually told that we basically in our lab tortured the droplets. So that is the correct way of saying that we tortured them. So we torture them, we deform them, we atomize them, we evaporate them, we combust them. Okay, so we do everything possible to the droplet, but it cannot complain. So, okay, so bad luck there. So I'm going to show a few examples before we go on to the main thing. So this is, for example, when you just talk about the evaporation in a droplet. So this was a new method in which there is a water droplet and there is an ethanol droplet. By creating a vapor field asymmetry, we were able to control the flow within this droplet. Why this is important? Because these kind of sessile droplets actually exhibit very low flow. So therefore, for biological applications to any other application, this is a very slow process. So you kind of sped it up by using nothing but the physics of the problem. This was from our COVID-related work, where we actually had a pathogen droplet, and we evaporated them, and we tried to find out what was the state of the bacteria or the virus at the end of the process. This is also a self-assembly of Klebsiella pneumonia when it dries on a substrate. I think Deepshika is aware. You've seen this picture multiple times. So these are actually how the bacterial droplets actually accumulate and how through the instabilities, how they form these very nice patterns. And this was also buckling of a nanocolloidal droplets that we did in the lab. So these droplets basically have particles, nanoparticles, and they show certain features called buckling, which is a solid mechanics phenomena, by the way, but you can see that at the droplet level. So these are all very slow phenomena. Let me put it that way. So this is the crux of the matter. This is slow phenomena. And then you have the physics of impact. So impact also you see in everyday life, right from your windshield all the way up to you prepare actually surfaces which mimics the nature like a rose petal or a lotus leaf. Okay, we have done those kind of work. We have engineered new surface microstructures with Ravi Broto at IIT KGP, and we have found out that how this droplet actually breaks and spreads and recedes. So this has got immense practical applications. Same thing happens when the droplet actually impinges on a shallow pool of liquid and it is immiscible. As a result of that, you get some nice phenomena like crater formation and other type of stuff. I'm not going to go into the details. And this is the mass study, and this is a recent one in which we tried to mimic the 3D printing aspect of it by using polymer droplets. So you can see if you impinge droplets across a hole, you can see how you can speed it up and how you can atomize it using that. But all these are again slow phenomena, okay? And well studied. This is the same thing in the combustion paradigm. You actually do the same droplet dynamics now with acoustic forcing, okay? And this is like basically a flickering flame. This is the same droplet flame when it is dropped from a drop tower, high down. And you can see the strange dynamics of the flame as it rolls and how it actually pinches off. So forget the theory part about what I have written there for the time being. So this is basically a vorticity buildup that actually leads to the, the severing of the top of the flame. So all these things were done again in combustion, again at the low velocity scale. So this is a droplet. I am all at low scale, slow process, etc., etc. Now you enter into the world of atomization where things gets a little murky, okay? And in atomization, for example, this is a nice little video. You can see a vortex, and this is a droplet. Can you see how it actually atomizes it, engulfs the whole droplet, stretches it, and then engulfs it, and then breaks it up, okay? So this was done by Shubham in that JFM paper that you can see over there, but it is a low intensity atomization. It's very well behaved kind of a system, so the atomization is never well behaved, but you can kind of see the structures quite beautifully. Okay, so you don't require that kind of high fidelity all the time. Okay, this gets a little bit more murky because this is done in a combustor. So you can see this is a liquid sheet which is flapping like this. This is what happens in your gas turbine combustor. So you can see there is a flow around it, and this sheet just flaps and breaks. As a result of that, you can see that this is a very strong base flow, okay, and the droplets are injected in that base flow, and they show this extremely, unique gamut of atomization phenomena. Okay, so this, what I call, you can see the Weber number. I will come to the definition in a little bit. This goes up to about 500, which signifies that there is an element of catastrophic breakup. So you are going to that regime where things will get really complex. So this is a moderate intensity atomization, as we call it, okay, in a gas turbine situation. This is a nice little video done by Siddhant and Jatin where they call it the droplet dementors. If you look at Harry Potter, if you remember, so you will see why he calls it a dementor. So you can see the tail of the droplet, and it actually interacts with a highly turbulent jet, and it atomizes and gives these fantastic structures. But again, this is also a moderate intensity atomization, but you can see the structures quite beautifully in this particular case. All right, so now we get to the point where we go to the droplets under extreme conditions. So this is where the story really gets very complex. Okay, so the motivation of the extremes is obvious. You want to use fuel injectors, you want to produce metal powder for your additive manufacturing. How do you produce metal powder? You basically put the liquid metal into a shock-laden flow, and therefore you get these small liquid droplets, liquid metal droplets, which solidifies and you form this powder. So in order to have a control over the powder, as Satyam and others will tell you, the powder size, more monodispersed it is, better will be when you actually you do this laser sintering and all those other things. So we need to have a control over that. So metal powder production, while it looks like that it is a problem that has nothing to do with fluid mechanics, it is actually has to do everything with fluid mechanics over there, okay? And spray coating, this is one other application that most material scientists know, because during my PhD I worked in a DARPA-funded project where we used to coat this using plasma-based, we used to call it solution precursor plasma spray process, and we used to coat the turbine blades with the precursors. So here both things happens. You have something called a primary atomization and you have something called a secondary atomization, which we are going to cover in details. What happens over here is that these droplets, how they atomize and how they move, how they disperse, how they atomize, actually signifies that whether your combustion will be better, your powder size distribution will be better, or your system is optimized or not. Everything depends on how well you atomize it. Can you predict, okay, or at least give an idea of what is going on over here? And this is, for example, a liquid jet in a supersonic cross flow. This is a drop impact on a Mach 3 projectile, so you can imagine the kind of velocity scales we are talking about. This is an actual metal powder production in what we call a closed couple atomizer. And this is the sheet atomization in a swirling flow, which I showed a couple of slides back. So these normally have this high-speed gas interaction, okay? Normally air, in some cases some other gases also. And you need to see that how they actually atomize. And this is not a trivial problem, okay? No matter what people say, this is a problem that is most complex. So let's look at a little bit into the fundamentals, because not everybody can have the background. So when a liquid comes out, okay, it first undergoes primary atomization. So basically the sheets and the jets atomize into the first round of droplets. Then these droplets, because they still see a very high velocity flow, they atomize further into smaller and smaller droplets. Okay? So this is the primary atomization done by Kupuraj, and these are the secondary atomizations that you can see. So understanding secondary breakup allows us to have the desired droplet size. We are far away from that in all possible conditions, but you can always manipulate and see what is the effect of this. Okay? So these are very red hot areas of research, okay, so to say. All right. So let's look at the important forces, because you are dealing with fluid mechanics. So basically you have the shear, you have the pressure force, you have the body force, you have the capillary effects and the viscous effects. Most of them can be summarized into a bunch of non-dimensional numbers. Fluid dynamics guys loves non-dimensional numbers. We like to project everything in non-dimensional space. Out of that, this Weber number is very important, because this signifies what is the inertia versus what is the surface tension. So essentially, if my surface tension force is high, my droplet is not going to deform. So I'm very resistant to external forcing. So that is the inertial force. Okay? Then, of course, Reynolds number is a very standard definition. And then you have the Onsorge number, which basically says that how the viscous and the surface tension forces are related. Okay? So when you study secondary atomization, just to give a very brief idea, historically what people have done is that you can understand that as you increase the Weber number, your external or your inertial forces become stronger and stronger, or your surface tension force is very low. As a result of that, you are more prone to breakup. Okay? So when the Weber number is moderately high, a little high, these droplets undergoes these nice vibrations, okay? And they cleave and they form this droplet. So this is very nicely understood. There is no question about it. You go a little higher in the Weber number, you actually form a balloon. So the droplet flattens into a sheet and the center actually blows. As a result of that, and then the balloon bursts and you form droplets. You can have something which is called a multimodal kind of breakup, which is a bag and stamen breakup, as they call it. Then you have, as you go on increasing the Weber number, you go to sheet thinning, and ultimately you go to something which we call the catastrophic. Other way of telling catastrophic is that I don't know what is going on. things are haywire. I cannot make out what is going on. So, first few things are very nice and easy. Okay, so I will just show you videos which shows what is going on. So this is a bag formation. This is Weber number about 12. You can see the bag. This is a bag and stamen formation, Weber number 44. You can see the stamen. And then you go and then you form the shear thinning, first instance of shear thinning, Weber number of around 200. Now, if you go to Weber number of 14,000, you can see, well, the hell literally breaks loose. Okay? Here you can see nice structures. Here, those structures are there, but it happens so fast. Everything is over. And this is 14,000 Weber number, real high. Okay? So to get to those higher Weber numbers is also very difficult. It's not a trivial job. Okay? So this is that there is a regime map proposed by Jerry Faith in 1995. He was in Michigan, Ann Arbor, very famous guy in multi-phase flows. He proposed this chart, which is basically a Weber number Onsorge number map, where he showed that how these breakups can be this is like a regime map. So you know your Weber number, you can identify what kind of breakup you can expect. Okay? But the point was that what I want to emphasize here, that it is insensitive to Onsorge number. That means for a fluid with you can go on increasing the viscosity, you essentially will not feel it till you cross a certain limit. And that is what happens when you till about 10 to the power of -1, you don't see the effect of Onsorge number, but things then starts to pick up as you go on increasing the viscosity and as you go on, say, for example, go to complex fluids and stuff like that. Okay? So he had this map, okay? And then I will talk about that why this map is not very useful. These are the reasons. The classification is based on a topology. Okay, so I see a topology and I say, okay, this is bag and stamen. Okay, I see something I cannot make out is catastrophic. So this is how I historically identify it. It doesn't have a physics-based intuition that you do not know what has caused that in the first place. And it spans only a very small band of Weber numbers. So beyond like 200, 300, you say everything is catastrophic. I cannot do anything. Okay? And catastrophic breakup, therefore, has a vague interpretation. What we are going to show, or just allude to that, this catastrophic breakup is a combination of, we will say what those are, Kelvin-Helmholtz and Rayleigh-Taylor instabilities at very rapid scales. And how they actually kind of reinforce each other, we will see that is what the word catastrophe actually means. All right. So let us look at what happens to the droplet. So this is once again a simple pedagogy slide. So this is like what is called a Rayleigh-Taylor instability. It is a pseudo body force, basically, where basically a lighter fluid pushes into a denser fluid. So this can happen under gravity, where the acceleration is g. It can happen artificially, where you can have an acceleration a. Okay, whatever that is. So this basically destabilizes the interface, and this is what we call Rayleigh-Taylor instability, named after Lord Rayleigh and G.I. Taylor. Okay, the middle one, which you normally see even in clouds, is basically called the Kelvin-Helmholtz instability, in which two fluids are basically shearing against each other. So basically here, by the virtue of shear forces and only resisted by surface tension, you tend to develop these wrinkles on the surface. This you can see even in the clouds, even at the atmospheric scale. The last one is called Rayleigh-Plateau instability, or RPI over here. So this is if you have a straight ligament or a capillary, it tends to develop this surface corrugations, ultimately leading to pinch-off. This you can see even in your kitchen sink. If it is a long enough ligament, it will start to show these instabilities and break off. So these are the three instabilities that are primarily responsible for what we are going to show in the next few slides. Okay? As you can see, it is all Rayleigh-Taylor, Kelvin-Helmholtz, and Rayleigh-Plateau. So the utility of us is rather low, because all things are basically done by these guys. We are just kind of reinventing a few things. Okay? So we do a reclassification, therefore, of the breakup modes. Okay? So what we say over here is that if you look at a droplet, right, it undergoes an initial deformation like this, because it is just facing a flow. Okay? It deforms. As it deforms, there are two things that can happen. There can be surface waves that can go near the equator, form these sheets. This is basically Kelvin-Helmholtz waves, and the sheet can break up. This is an example of that is shown over there. It can also do one other thing, because it's a heavier, lighter fluid combination. there can be, depending on what is the wavelength of that instability, you can form this thin region where you can form these bags. This is a very typical example of a Rayleigh-Taylor piercing. So the example is shown over there. Okay? So these are the two ways. So what we say, Rayleigh-Taylor piercing is basically dominated by Rayleigh-Taylor instability. We call shear-induced entrainment, which is light here, it is dominated by Kelvin-Helmholtz instability. Okay? So this is what happens when a droplet faces an airflow, okay? Depending on whatever the instabilities are. So this is how it happens. From vibrational to multimodal, part of it, it is always Rayleigh-Taylor piercing. From multimodal to catastrophic, it is always shear-induced entrainment, which is basically dominated by Kelvin-Helmholtz. Story is a little bit funny that when you look at SIE, which happens at larger Weber numbers, you see this Kelvin-Helmholtz waves. This is very high fidelity imaging done by the group, where we can see that you can clearly see these surface waves. They then form sheets, and the sheets form ligaments, and the ligaments forms droplets. So this is primarily dominated by Kelvin-Helmholtz. But hang on, if you look a little carefully, if you look at the droplet from the top, you can actually see that there is a lot of azimuthal instabilities as well. So instabilities that goes like this. These are on the Kelvin-Helmholtz waves. So you imagine that there is a pattern that is created by the Kelvin-Helmholtz, and in that topology, okay, the Rayleigh-Taylor waves are actually getting superposed. Okay? So this is the azimuthal RTI. And then you have a longitudinal RTI also. These are typically of low growth rate waves. So when you talk about shear-induced entrainment, it is primarily driven by Kelvin-Helmholtz, but there is a Rayleigh-Taylor component to it always, and we will see how. Okay? So this is what happens at this particular stage. Now, on the top of that, if the flow is too fast, what can happen is the Mach number effect. Basically, another way of telling this is the compressibility effect. What happens is that the compressibility changes something which is called the boundary layer around the droplet. Okay? It also affects the boundary layer. It can have a bow shock in front of it. So bow shock is like a shock like this. It modulates the flow field. As a result of that, interestingly, when you think about high Mach number event, you think about the flow is very fast, you would have a very catastrophic breakup, but the degree of catastrophic breakup is actually suppressed to a great extent. This is what we have seen, what other people have also seen in their work. So this is the compressibility effect. Okay? So therefore, we restructured this map in this annual review of fluid mechanics paper just out, where we actually showed that, this is done by me and Jatin, okay, he more being him than me. Okay, so this actually shows that you can revisit the map that was done by Jerry Faith earlier. You can now show the different modes in a more classified way. Now it is SIE and RTP type of modes. You can reclassify those modes on the top of what Jerry Faith actually did. In addition to that, you can have an extended axis. So now it becomes a three-dimensional map where you actually plot the Mach number effect. So these maps is essentially three-dimensional in nature. Okay? But this still, it captures that what happens from an instability point of view, but it does not tell you that how this breakup physics actually happens, the transient dynamics of the same. For example, if you look at this versus this, how does this transient dynamics can be captured? Okay? What can be done? And what is the spatiotemporal scales involved in such breakage? Okay? So that was still, but this is still an interesting map which can be used instead of the Jerry Faith map we had like roughly 30 years ago. All right. So now, in order to do that, you can have three experimental configurations if you really want to traverse all kind of conditions. One is the drop tower, which I already showed. Okay. This was a paper by Emmanuel Villermoux in Nature Physics. And this is basically a jet. So you can just drop the droplet, and it sees a flow. As a result of that, it will undergo atomization and whatever. But the Weber number that you can get is 10 to the power of 0, essentially, of the order 1. This is a continuous jet, and you are injecting a droplet in a cross flow, like what Siddhant did over there, and Naveen did as well. So what happens over there is that you can go up to about 100 quite safely, maybe 200. Cannot do more than that. You need a shock tube, therefore, where you can go up to a Weber number of 10 to the power of 5. So we are talking about 3 orders of magnitude higher, there you can see all the beautiful physics that will come out. So we have all 3 of them, but we prefer to use this. Okay? So this is what shock droplet interaction is all about. So we have our own shock tube over here. So you can see once the shock comes, and it is accompanied by a compressible vortex ring and a trailing jet. So the droplet is placed right over there. We were a little imaginative. So what we did was that we actually had the droplet in an acoustic levitator. We positioned it spatially, and the shock came and blasted it away. So there was no positioning thing. So there was no timing that was required. You could just held it in position and blast it. And this shock tube operates in whatever configuration that you want. So what it happens is that you basically melt a wire or vaporize a wire, and the shock front actually passes. So this is what happens. You get a compressible vortex ring and a trailing jet. Now, this enables you to go up to, by using different contraptions, different types of channels, you have a capacity to go up to Mach number of 3, and you can have a Weber number capacity of 10 to the power of 5. Okay? And the footprint of this entire thing is right about half my size. That's it. Okay? So that's it. I don't need any additional space. Okay? So what happens is that, now this is the global view, what happens when a shock droplet interaction happens. So this is a droplet, this is the incident shock, this is a Weber number of about 500. You get the shock, passes through the droplet, and then you get the reflected shocks and all those things. You can see nothing happens to the droplet. The shock has passed, the droplet retains as if nothing has happened. Shock wave itself, when it passes, doesn't have any influence. The droplet breakup happens due to the compressible vortex ring that kind of succeeds it, the trailing one. So there what happens is that for the same Mach number, okay, you can have a Weber number of 94 versus about 500. In one case, you get shear-induced breakup. In one case, you get Rayleigh-Taylor piercing. Very accurate control on what regime you basically want to study. So these are all with normalized time. The time has been normalized by the air velocity behind the shock. And the stages are, the first stage is microsecond, the other 2 stages are milliseconds always. Okay? So the first event happens very fast. Okay? And you can modulate the droplet diameter to change the Weber number. Okay? So this is what happens. So you can see for 3 different Weber numbers going from 1300 to about 10 to the power of 4, okay, you can see that there is this Kelvin-Helmholtz waves. You can see that very clearly, and droplet deformation, whatever we said earlier, right? Okay, so if you look at the picture, these images I'm really proud of. So to take these images at Weber number of 2000 required all credit to these guys. Okay, so they are excellent experimentalists. So what happens is that you can do a linear stability analysis on this, but normal linear stability analysis, what it does is that it takes into account a 0 vorticity thickness, which means that there is a slip at the interface. Okay, so air velocity and the liquid velocities don't really match. Okay, so as a result of that, you get a significant underprediction. Okay, so these are the experimental values that you have. Okay, but then if you take a finite vorticity thickness, that means essentially you take the boundary layer into consideration. Okay, on both the air side and the liquid side. Normally the liquid side you can ignore, and the air side you can use. This is a finite vorticity thickness. You get a very decent match. So a simplistic analysis gives you an idea that how this Kelvin-Helmholtz waves actually propagates. Okay, so that's good. So you also see now the Rayleigh-Taylor waves. As I told you, from the azimuthal direction, you can see the waves. You can calculate the wave number. You can also do a similar linear stability analysis. And you see from an order point of view, the predictions also match. So you can really also predict the Rayleigh-Taylor waves also. But these are very global features. These are the first round of deformations or the first round of Kelvin-Helmholtz waves that you get, okay, on these droplet surfaces. Okay? So you might want to say that there is another thing that actually governs this whole physics. It is called the compatibility criteria. Remember this plot once again. Now, if I showcase this, okay, so this is the droplet diameter normalized by the Kelvin-Helmholtz wavelength. You see in a certain domain, which is roughly around that Weber number less than 1000, you can see that you can have both SIE as well as RTP. Now, you might ask why. That is because when the droplet size goes too small, okay, the Kelvin-Helmholtz waves cannot grow. As a result of that, they are suppressed. So this droplet continuously deform, and then you have the smaller growth rate RT waves actually taking over the show. Okay? So this is what we call the compatibility criteria. So you need to be compatible. Though the Kelvin-Helmholtz waves are always faster, but since you do not have a space, you have a space issue, or basically you have a length scale issue over here. So these RTP waves are, and the number of RTP waves that you can have on that deformed surface determines the number of bags that you are going to have. Remember that multimodal bag breakup that we talked about. Okay, so this is the compatibility criteria that we talked about. Now we try to answer that what happens when you go to other types of fluids, complex fluids, liquid metal. Does this criteria hold? Does this narrative actually holds? Okay, so do they exhibit similarities in the mechanisms? Okay, I think that is a very legitimate question to ask. Indeed, this is water, Newtonian. This is a polymer. Okay, the spectacularity of the picture, if you can just get around it, and this is liquid metal. Okay, so you can see two things. The final topology of the breakup is a little different, but the mechanisms that actually initiate these breakups are essentially the same. Okay, so visually they look similar as they break, but is there a universal picture to it? So this is like when you increase the polymer concentration. This is water. So all that happens is that if I just play the front end of the video, you will see that they are more or less deforming in the same way. The waves are appearing in the same way. But the final morphology actually varies. This jellyfish type patterns is inherent because you are using the C by C star. So basically you are increasing the elasticity of the polymer. So it can stretch more essentially. So this gives us an idea that we can now develop a regime map which is dynamic now, which has a transient history, a pathway rather. So instead of just a point where I just bucket the structure and put it over there, you can predict a pathway. So this pathway is as follows, that you have a deformation phase, then you have a low Weber number which leads to vibration, moderate Weber number KH waves, high Weber number you get both KH and RT waves. And the final structure over here is a little different because up to this, stage 1 and stage 2, it is universal. It is applicable for most types of fluids. The last part is where the topology, which is basically the topology, is determined by the elasticity number, is another way of telling how elastic the fluid is. Okay? So that is a story for another day, okay, that how we analyze that and so on and so forth. All right? So this gives like an even more complicated regime map that you can see here. Normal regime maps, you have this Weber number and other things. Now you have an elasticity number going up on the top. So what happens is that with time, how these modes actually proceed. So these are basically time snapshots. I take a camera, I take a snapshot, okay, at different instance in time. Then I basically plot the trajectory that how these things actually go to the final form. So this is pretty new. This is a temporal regime map, therefore, very unique and very interesting because it addresses the actual route through which you can go to the breakup. So you can therefore say that the breakup modes are governed by the Weber number, but the breakup morphologies may be dependent on the elasticity number in case of polymer. In the other cases, it may be dependent on Onsorge number to a certain extent if you have a high enough Onsorge number, and so on and so forth. Okay, we did it with liquid metal, and essentially you get the same physics out of it. So I will just go back. So this is the liquid metal, as you can see. So if one of them is actually water. Okay, so if I take away the scales, that this is water, air, this is Galcian, you won't be able to make out which one is which. So essentially they follow the same type of breakup modes, same type of behavior, and so there is a certain amount of universality in their temporal passage. So as they march towards their final breakup condition. But what we have established, we established the breakup modes, the breakup mechanisms, a revised static and temporal map, the effect of liquid properties, which is basically the polymer and the liquid metal. And in the future, you want to have a regime map that includes these temporal elements. But then, this is not all. In the last part of the presentation, what we are going to do, we are going to look at the multi-scale deformation and the underlying mechanism. So here we go probe a little bit deeper and try to see what is happening. Okay? So this is what we call the evolution mechanism or the geometry, how this actually goes. So let's look at a breakup. If you just look at this breakup, I have shown enough number of images on this, you will find that apart from this longitudinal instabilities, azimuthal instabilities, you have holes, you have sheets, you have droplets, right? This you see in this computational study, as well as you see in the same thing in our experimental study, right? Let's establish the level playing field that we are talking about the same stuff, okay, over here, okay? Now let us look at a closer look at the stripping process in itself, right? So this is a disintegrating droplet. This is the droplet which actually disintegrates. So what it happens, it becomes flat. First thing first. Okay, so you have an incoming airflow which has got a nominal flow velocity of u naught, and then you can have any type of unsteadiness which can come out of perturbations in the flow or turbulence or whatever. So this flow is attacking this particular deformed droplet. But because the droplet is now deformed, what happens is that this deformed droplet now starts affecting the airflow. So the airflow starts developing a velocity scale which is ud prime, because you have an obstacle. This obstacle is now modulating your airflow field. It's like a two-way coupling process. Now, on the top of it, you see this smaller perturbation that starts to appear on the surface. These are the different wavelengths. And the air, as it goes around this perturbation, faces smaller and smaller hillocks. So you can imagine there is a big hill that the air is climbing. As a result of that, its velocity is changing. Now, in the hill, you have this topology, subtopologies of the hill, where the air is moving up and down like that. Okay? So it's not a very smooth interface, right? So the air is climbing this interface like this, okay? So therefore, if I zoom into that, what happens is that locally, you have a Weber number. It's not the global Weber number, it's a local Weber number, because it's a Weber number that a small undulation on this droplet surface sees. What is the flow, the local flow there? And it has got a deformation length scale, which is given by that, okay? And say this is the ith, or I+1 deformation. What happens is that this particular sheet now, after some time, it basically atomizes and forms a droplet, exposes a new surface, which again now goes through the same cyclic process. All right. So this is the fragmentation what happens at this local Weber number, which leads to this droplet getting generated. So these are all the symbols that what kind of nomenclature we actually used over there. Look at this particular thing where we talk about this local velocity scale perturbation. It's a summation of many such small perturbations in velocity. All right. So this is what happens. All right. So what I am trying to say over here, that these waves undergo a cascade procedure. So it goes, breaks up, again grows, breaks up, goes, breaks up, and it happens at multiple length scales. It's not just one single scale that actually governs the whole problem. Okay? And whatever mass remains, that changes the global Weber number, again it changes the local Weber number, again it becomes smaller, and this entire cycle goes on repeating. Okay? So if we look at this cascade a little bit closely, you will find that this was the original droplet. Okay? Now this has got perturbed like this, so you have all these eddies that are created behind the droplet. It gets deformed more, you have further eddies. These are global droplet level deformations. All right? Now you take one part out of it, you will see that there are these local signatures, these local Kelvin-Helmholtz waves. Okay? So this is what we call the generation 2. That is generation 1 deformation. This is generation 2 deformation. You look at this particular thing closely, you will see that there is a hill, local hill. The air accelerates and retards across that hill. The hill basically grows because it's an instability. It is stretching it. As it grows, the air is modulated further. So you form basically a liquid sheet in the whole process. So this is a transient process. Then you go to the azimuthal view of this, that means on this other side, you're looking at it from the top, you will see that these sheets that are growing is actually a little bit, it's not straightforward like that, it's a little curved. So you have a sheet which is expanding like this into another fluid. You have variation in curvature across the top. This leads to the Rayleigh-Taylor instability. So this rim that you see in this direction now has got waves in the other direction. Okay, so it is not a straightforward that this goes on to infinity. This has got wrinkles that goes around it. Okay, so now locally it forms a bag. Okay, so this sheet now forms a bag. This bag now breaks and forms these droplets. So you can understand this bag formation is not the big bag formation that we are talking about. This is bags that are forming at that local length scales, small bags. Okay, and ultimately it forms the bag ruptures, it forms the ligaments, and the Rayleigh plateau instability, if you think about it, this basically terminates the ligament to generate the droplets. This is what happens fundamentally at the different generation levels. All right? This is what we call the sub-secondary breakup process. This has a self-similar behavior. Okay? So this is marching on to even more, territories which people have not looked at. Okay? So if we look at this closely, once again, these were the oscillations in this direction. If you look at it from this side, you will see that this is the local air velocity. These are a combination of Kelvin-Helmholtz and RTI crests. So I can define a local Weber number right over there with this local velocity, as you can see over there, need not be the same as your global Weber number. Now for SIE, for the global deformation, which is this deformation, okay, that should be scaling as the droplet diameter, because these scales should be similar. These local perturbations are much smaller than the droplet diameter. So these are what we call the sub-secondary kind of breakup physics. So we can treat each of these undulations that you see over here as a segment of a droplet, and you can use the local breakup dynamics to see what kind of droplet it generates. That is the procedure. Okay? So after certain generation is over, this Weber number ultimately will fall to about 1 or 2, right? Okay. So there you have the viscosity coming into the picture. The droplet will cease to break. Okay, so this cascade continues till the viscosity kills it at some particular level. Okay? And the cycle time of this wave mechanism you can calculate very easily. It is the growth rate of each of this, okay, by 2 pi by the growth rate, which is basically one cycle. What is the time scale? Now in catastrophic breakup, these cycle times are so small that overall you see just a murky picture, that everything is going haywire. Okay, but this is exactly what happens at those small scales, repeatedly. All right, so this is what we say, that the early stage cage induces an undulation, then beyond a finite amplitude, this destabilizes, and subsequent wave mechanisms, okay, are what we call a nonlinear wave cascade. This has got the azimuthal RT, and the dominant direction basically determines what kind of rupture events you are going to have. Okay? So this cycle repeats itself till you actually have the Rayleigh plateau instability, and the droplet is basically torn apart. So this is what happens at the small scale. Remember, this bag, these rims are very different from the low Weber number events that you see. Okay? So, and this we were one of the first to propose this kind of things, okay, in the annual review as well as in a companion JFM. Okay, and these are the visual images. Okay, this required Jatin quite a bit of an effort to zoom in at those kind of positions, and you can really see the RT crests, you can see the ligaments, you can see the back rupture, you can see the ligaments from the rim. All of this you can see at that small window, and this is not at the big drop level, it is at that level. Okay, and this requires literally thousands of experiments. It's basically a fishing expedition. You sit there and you collect data. Go on collecting data. The hard part of being that you have a theory, okay, how do you validate it? Okay? So another thing that happens is that these ligaments are all very corroded, are all very corrugated, because these events can be turbulent, the ligaments are not smooth. So, and when they actually break, these are the droplets that are produced. These are the droplets what you see downstream. Okay? So these are not straightforward, nice ligaments that you see at low Weber number. They're very nice ligament, but it breaks up and everybody is happy. It's not like that. Okay? Okay. So this basically summarizes the evolutionary tree of the whole thing. Unperturbed droplet, global deformation, KH waves, subsequent deformations are superposed. This flow undulation creates what we call the mini wakes, mini whirlpools. Then the top view suggests that it forms these sheets. The sheet can rupture, or RT waves can develop. This can grow and form ligaments. If they are at a slower rate, they form these bags, and the bags ruptures, and the rims develops this droplets. All of these are ultimately ends with a ligament-mediated breakup. Okay? So what turns out over here is that what we thought that there are these corrugated ligaments. Let's find a way. Can we see that whether there is this self-similarity in the droplet size distribution after all? So you have the droplet size measurements. Now this turned out to be very hard, because anyone who has tried to image an event which is impulsive, that means there is a shock wave flow and after that everything is gone, you cannot use traditional equipments like PDPA, which is phase Doppler anemometry. You cannot use that. So you have to use something which can record this high speed flows, but at the same time it is able to give this droplet sizes. So we did a method called depth from defocus technique, okay, using 2 cameras and also single camera. Okay, it's for another day. It's a complicated measurement. We have a patent on this as well. So basically what you can do is that, cutting a long story short, you can measure the droplet sizes. And how you can measure it? This is the example, 900, 2000, 4000. So at that level, where you can hardly see anything, you can measure it at certain temporal buckets. So these are like time scales over which you collect the data, and you are able to find out the droplet diameter as well as you can find out the velocities. Both you can do. Okay, so this gives us the utility that what we are actually looking for. So these are the overall measurements, these are the bucketed measurements that you see. PDPA cannot do, no technique can do actually, apart from what we said over here. And indeed now, if you take this to be corrugated ligaments, and there is this, what we call this corrugation diameters, and if you construct a compound gamma distribution of this, where keeping in mind that this n, which is basically the mean corrugation diameter square minus this, okay, this particular thing actually has a theoretical limit of n to the power of 4. That means at very high Weber number, this becomes 4. So therefore, this graph, nothing changes after that. So if you fit the distribution, they actually do follow a self-similar path. Whatever deviations that you see at the end is because of the decaying flow field. So if this flow field would not have decayed, it would have remained the same. There are also events like coalescence, then 2 droplets colliding with each other and forming a major blob. So all these things we can, these are the things which basically shifts the distribution towards the right. But this is a piece of good work, and we are probing further into this. That has happened. Okay. You can extend these ideas further. This is currently what we are working on, that how do you model this corrugation over the ligaments, and can you have a regime map for the subsecondary breakup processes? Extraordinarily hard problem. Again, these corrugations are very, very hard to image and to do this. Then you also, this is a nice video, if you can look through it. So this is basically a liquid column atomizing. So this is also, you extend this flow configuration now to a liquid jet, okay, and you see that whether this cascade mechanism is still valid or not. So you can also establish the transient dynamics. This is something that is going on. So this is almost like a turbulent multi-phase kind of a system. And the last thing, kind of a holy grail, can you find out the scaling laws for this cascade behavior? Is that possible? I mean, is that possible at some level to do that? Okay. So moving along, we did not stop here. We also did this same thing now, a droplet combustion paradigm now, where when the droplet flame actually interacts with the shock. And this is a rather interesting work in which, because these are the days where fluids gets fancy, that means you can have slurry fuels or fluid which has got mixed additives into it. So what happens is that if you keep a fluid for some time into open air, due to evaporation, it tends to form this shell or gel type structures. So how does those gel type structure interact with a high speed flow, and does it change the breakup mechanism, and is there some universal laws that govern that as well? So these are the current work. I mean, these two are published in JFM. There are more work that are going on for microemulsions and other types of fuels, other types of fluids, okay? And even fluids which are fancy, like fruit pulp, anything that you can think of. Okay, what happens with respect to those? Okay, so conclusion, We have established the subscale level breakup model, the multi-scale cascade, the ligament-mediated droplet generation, the physics of the same. There has been work on this in the numerical side, also at the experimentally pretty robust experiments. And in the future, we do expect this regime map and perhaps have an intuition into the turbulent multi-phase system and the wave cascade. Can we do that? Let's hope, and we'll continuously work and see. So these are the papers. There are quite a few. Okay, so not going to bore you with that. And lastly, thanks. Thanks for your time.
Dr. Basu, for taking us through the fascinating journey of a droplet. It was very educative, at least for me it was really very educative. So are there any questions from the audience?
So I really enjoyed the talk very much. Thank you. I was curious about the effect of evaporation. Doesn't happen at all in these cases? I mean, you didn't talk about...
evaporation is basically a slow process. If you look at evaporation...
So in these time scales
it doesn't matter.
No contribution.
What can happen is that, what I showed in the last slide, say for example, you have a liquid droplet which has got some, say it may be bicomponent. So it can have a degree of volatility or it can have particulate matter. So once it evaporates a little, say in a normal flow condition, then it encounters a high-speed flow all of a sudden. Then the breakup mechanism can change. But when evaporation and this is competing simultaneously for the same pot of pie, evaporation is a loser because it's a very slow process.
So even if you do it with a liquid like ether, for instance,
it doesn't matter. It is very normal evaporation is very slow process.
Correct.
So, but this shock, as we say, this is a millisecond, microsecond order event. So everything gets over before you know. That millisecond doesn't even shrink the droplet size by any detectable limit. Low flow rates, when you have actually a base flow which is kind of not at a low Weber number, yes, perhaps you can have some effect of evaporation. But definitely evaporation can have a role when the droplet has evaporated a little bit. But then you are kind of changing the initial condition, what you are putting into the system. Yeah.
In most of your examples, the droplet is in a very low density fluid, like air, right?
Yes, air. Well, we have done it for others also.
So if you do one liquid in another liquid and do the same experiment.
Yeah. There was this video that I showed, which was a liquid in liquid also.
But with this high flow rate, I mean.
High flow rate. Yeah. So you can do all those kind of. In fact, liquid in liquid is a little bit easier to do, but liquid in air is because of the density contrast. It's a very difficult problem.
Hi, Saptarshi. Yeah. So you described something with elasticity number something. What was that? Is it zero frequency elasticity or is it like or relaxation constant based number?
It's a relaxation constant based. Okay, but I just showed it over here, but we can have a more discussion on that. I mean, it takes into account that I do not have the slide over here. I can show you the exact expression.
So it would be very large because these are very short time scales that you're looking at.
Yes, but so that's why the first two stages elasticity does not even play a role. Because if you think about the Onsorge number concept, I mean, in the elasticity Onsorge number kind of a space, the first two stages are so fast, okay, and so subtle, it does not have any effect. It is only at the topology phase when you are actually having stretching, because now these ligaments are now getting stretched, okay, after it has come out. Okay, there your liquid properties, like if you put a honey, for example.
I think there is another thing happening there, which is because the momentum transfer is happening, the effective force that aerodynamic force that they're feeling is continuously very rapidly going down.
Yeah, it is.
And
it is because it's a blast wave.
No.
Yeah. It is a blast wave because, as you can see, that if you do it in a conventional shock tube, this will last forever. Okay, but here, in a realistic situation, this is an impulse. So that's why it is going down, obviously. So there, as you go down, the elasticity or the viscosity, whatever you call it, that comes into the picture. That's true.
So if you compare these shapes that you're getting for polymeric fluids with the initial shapes that you get for a Newtonian fluids, this formation of number of ligaments and
so that analysis has not been done. Okay, so you are right. So we compared the breakup or the instability growth and all those things, but comparing the Newtonian with the non-Newtonian. Okay. First we thought that subsecondary should be done for something that we have a very clear understanding, that is the Newtonian. So that's what we did. But yeah, that is one thing that one can actually do.
What I'm getting to is that if you look at, because you talked about transient effects, and I think what is maybe there's a second layer of transient effect, which is effective Weber number decreasing rapidly.
Yeah.
Therefore, something that you expected to go into shear breakup mode would become into back breakup.
Yes, that also we have done. I did not show it over here, but those things have been also done. The first stuff that where you actually have the breakup, now if you let it hover enough, okay, you will actually see the shift in the breakup modes that can happen. Okay. So it's a complicated problem, as you can see that, but we first wanted to make the inroads right down to the subsecondary level where we actually have the cascade and all those things ironed out. And then of course, you can, and this is a very realistic situation. Unlike conventional shock tube, it is very realistic situation. But yes, but there are a lot of things that needs to be done. Okay, that universality with respect to complex fluid is something of a different ball game, and we want to go into that. Okay, hopefully we will at some point in time. Okay.
Professor James, you wanted to ask something?
What is the smallest size of the droplet that you have?
We have anywhere between 300 microns to about 3 mm. Right. Okay, maybe, yeah, maybe, possible.
Any other questions?
Yeah.
Yeah.
I agree with your student that you torture droplets. Almost looks like you should have droplet ethics committee in the institute.
Yes.
But anyway, instead of torturing a droplet, how about nurturing it? If I want to retain the droplet for a longer time, rather with all these insights, where do you use it?
So see, where you want to kind of suppress breakup and stuff like that, that is also another area of research. But the areas that we talked about, you want the droplet to atomize and you want to become finer and finer and finer and finer. That is the objective. Okay, now once you want to kind of retard that breakup, there are ways to actually do that as well. Okay, but it's a little bit more complicated. Okay, so, and well, there the fun is that nothing is happening. So you don't see anything happening. So there is a flow and all those things, the droplet does not deform, or it deforms, it goes back to its original shape.
Even under those conditions, you don't want it to.
So in that,
even under those conditions, you don't want.
Yeah, but here I think if you put sufficient amount of high velocity, things will break. You cannot help it because this is a basic tenet of the forces. So you have only surface tension as a lone player, and you have tremendous amount of inertial forces that you are putting into it, and all these instabilities, they are most of these things are unconditionally unstable. Well, there are certain wave numbers which you can kind of take it out just because of the surface tension and other effects, but these instabilities are ubiquitous, so you cannot help it, and they will grow. Okay, and the fastest growing things is what is going to lead you to all those bags and crests and all those things. So you cannot stop it, okay, wholly, but you can certainly retard it. Okay, but how to retard it? Because your inertia is so high, how do you, what actually stops the droplet from, not deforming? So one part will be that you increase the surface tension, but then is so much that you can do. It's a property, so you cannot do much with the surface tension either. Right. So other is that you make it very viscous. That is also possible because the damping effects will come later. It will deform. The waves will grow, but then the waves will attenuate also. So that is the thing that we are talking about. Okay, so that can happen, but then very viscous things might have other connotations. So we may not want viscous things. Yeah, fruit pulp and other things, even the mucus that coming out of my mouth when we are doing the COVID modeling, this is also viscous, because if I have a high degree of flame in my body, then it will come out to be very viscous. But even those deforms, you put, because we calculated when you cough or sneeze, this is about 40 meter per second. Sneezing is 40 meter per second, which is, if you translate into a Weber number space, it goes into the breakup, no matter what your mucus can do. So, you can only control the size, the amount of breakup that you will have, but you cannot really control anything else.
Thank you.
Sir,
yes.
hi sir, nice talk. So I was just wondering, so I work with two-phase systems.
So I was wondering how much of this regime can you shrink or expand if we play with the viscosity ratio, let's say, of the continuous phase which we are having in the system? Because they can suppress or enhance these instabilities which happen, right?
So viscosity ratio actually to some extent it is inbuilt into the Weber number, Onsorge number paradigm. So out of for a certain band of Onsorge number, which I think answers which also Anand Suresh was asking, that up to that it is basically non-responsive. I mean, viscosity doesn't do anything. Whatever you do it's about 10 to the power of -1. You can convert that to whatever viscosity that you have with respect to water, say for example. If you go to really high viscosity, you can see the curves actually going upward like that, right? So that means the same stage is now reached at a higher Weber number, that you need to push it more to break it in the same way. Okay, so unless you cross that threshold, this insensitivity comes into the picture. Viscosity is normally a delayed effect. That's why everything that you see comes in stage 3. Yeah, it doesn't really, okay, the viscosity ratio in that way, if they are very close to each other, okay, well, oil and water we did, which doesn't have that kind of a significant difference in viscosity, probably. We see the similar type of breakup mechanisms, right, guys? I mean, these guys are more clever than me. They would be able to answer your questions better. Okay.
Okay, so we have to stop here now. I think after this we will have a tea session and there a lot of discussions can be done. So with this, I express my sincere thanks to Professor Saptarshi Basu to give such a enlightening talk. And on behalf of the directors, I would like to present him a bouquet. Thank you. I think there is some tea organized outside, so just go ahead.